Hello, everyone. This is Siyavash Ebrahimian. I'm an author, researcher, and designer of this project. My project is about analyzing the offshore pipeline. It means doing stress analysis by simulation method. I use two simulation softwares, included the SolidWorks FEA or Finite Element Analysis, OrcaFlex Dynamic Analysis, as well as calculating the engineering mathematical and calculations. In these presentations, I'm going to talk about the abstract, introduction, material properties, methodology used, OrcaFlex dynamic analysis, SolidWorks finite element analysis or SolidWorks FEA, result comparison, and at the end, I'm going to talk about or discuss about the conclusion and recommendation. In the abstract, based on the U.S. Federal Energy Regulatory Commission or US FERC, the average inflation cost to install the pipelines from the year 1995 to 2014 in the Gulf of Mexico is around $3.3 million per mile or $2.1 million per kilometer. It is a huge number. Anyway, for minimizing any injury, damages, financial, and time waste, we need to use computational analysis and simulation methods. In this project, considers details of the SolidWorks FEA and OrcaFlex dynamic analysis to simulate the failure behavior, the effect of waves and forces on an offshore pipeline, as well as engineering mathematical hand calculation, which is SolidWorks equations, solid mechanics equations, the dynamic variables such as the maximum volumetric stress, stress at node 20, maximum bending stress, and maximum displacement are studied under the effect of waves and forces on the subsea pipelines. In the introduction, the offshore drilling is a mechanical process where the oil well is drilled below the seabed. The drilling techniques of offshore, inshore, or on land are not that much different. The main difference is that machines and facilities are used to excavate the oil and gas. Subsea pipelines are one of the most efficient and economical models to transport energy, and failure behaviors in the submerged offshore pipelines are one of the subsea pipelines are one of the most efficient and economical model to transport energy, and failure behaviors in the submerged offshore pipelines are one of the catastrophic occurrences that we hear often in the news that cause financial losses for companies and environmental damages on the massive scale of offshore drilling into the ocean waters. Therefore, the designing, installing, inspecting, and repairing of the pipes are the main jobs of the offshore industry. Again, designing, installing, inspecting, and drilling and repairing is the main job of the offshore industry. The installation of the pipeline at the bottom of the ocean is so complicated and way different from the outside of the water because some other factors are included. Those factors are weight of the pipe. We know the weight of any items inside the water is way lighter compared to the outside of the water. Wave velocity, water pressure, and we know when we goes deeper, the pressure goes higher. Buoyancy forces, we know the direction of buoyancy forces is upward, is exactly opposite of the direction of the weight of the item, which is downward, and also vibrations. So the stainless steel offshore pipeline is laid down on the seabed level at the water depth of 80 meters. And it has a valve in the middle located on the top of the pit. The weight of the valve and the effect of waves on the pipeline are analyzed by SolidWorks FEA and OrcaFlex, as well as solid mechanics mathematical hand calculations in this report. So in my project, this figure is my pipeline figures in this project. But before goes through the presentation, I want to share something with you guys. Yes, this is my figure this is the offshore pipeline and the valve is located in the middle. But however, in the SolidWorks FEA, I did not design the valve in the middle of the pipe because of preventing any computational error when I apply this, when I running the simulation. Because when I design the valve, because of too much assembly parts, the computer, the software, which is SolidWorks, get errors and it doesn't work to give me the final result. That's the reason I applied the normal force to the middle of the pipe where the valve is located. And I use that value of the force from the OrcaFlex dynamic analysis softwares. So anyway, let's go to the next slide. So in this slide is about the material properties. The material properties of the pipeline that I designed in SolidWorks FEA and OrcaFlex is AISI 316L stainless steel. We know the AISI stands for is American Iron Steel Institute. The reason I use this stainless steel material is because this is more significant yield strength and prevented the offshore pipeline from oxidization. So in this slide, we have two charts. So these are the dimension and material properties that I use in the SolidWorks, and I inspired all these data from the SolidWorks and I use it in the OrcaFlex analysis software. So this is the pipe that I designed on the SolidWorks FEA, and this blue chart is the dimensions. So the external diameter of the pipe is 323.85 millimeter. Internal diameter is 300.85 millimeter, and total length is 20,000 millimeter, which is 20 meters. The elastic modulus is 200 gigapascal. Poison ratio is 0.265. Shear modulus is equal to the 82 gigapascal. And the yield strength is 17 gigapascal. So I use these data and informations from SolidWorks FEA to the OrcaFlex dynamic analysis software. So methodology used. Using SolidWorks pipeline model dimensions and material properties in OrcaFlex model, and using OrcaFlex material properties included the weight of a 60 buoy. 60 buoy is the valve inside the OrcaFlex dynamic analysis software. So included the weight of a 60 buoy in the water as a normal force in SolidWorks pipeline model. Comparing the OrcaFlex result of maximum volume stress and a stress at node 20 with SolidWorks results, as well as comparing engineering or solid mechanics mathematical hand calculations final values with OrcaFlex maximum bending stress and SolidWorks maximum displacement value. This equation is the equation of the maximum bending stress, which is equal to C. C is the distance between where the normal force is applied and origin point. M is a bending moment, then divided by the I. I is a moment of inertia. So moment of inertia of each shape based on the geometry is different from other geometry shape. Third picture is a theoretical picture of my project, where this is the place or location where the normal force is applied. We know the normal force is applied to the middle of the pipeline. And then the two ends of the pipeline, input and output of the pipes, are attached or fixed to the seabed level. And this blue color shows how the pipe is bending. So in the OrcaFlex dynamic analysis, the OrcaFlex 11.11 is a software which is used in this project to get the accurate and high quality analysis result in a short processing time. The values such as the maximum volumetric stress, the stress at node 20, and maximum bending stress are used to validate the OrcaFlex static and dynamic analysis case. We know in the OrcaFlex, I use two cases. One is dynamic and other one is a static case. In dynamic case, we know the behavior of the pipeline was studied under the wave and current excitation. However, in the static case, the magnitude of stresses are analyzed without the influence of waves and current interaction. The OrcaFlex predicts the dynamic behavior of pipelines in the depth water. And we know the OrcaFlex software is usually used in a submarine systems. The OrcaFlex will be one of the most useful dynamic analysis method to make an engineering simulation analysis result before starting the practical installation. So this slide shows the steps I use in the OrcaFlex. And these data that we are looking at are data that I use it from the SolidWorks FEA inside the OrcaFlex. For example, the outer diameter, wall thickness is the outer diameter, wall thickness, Young modulus, which is also called the modulus of elasticity, Poisson ratio, material densities, and so on. They are the data that I use from the SolidWorks FEA. And also here shows the two ends of the pipeline is anchored. Anchor means attached to the seabed level in the OrcaFlex. And this yellow figure shows the weight of the pipe outside of the water and the weight of the pipe inside of the water. For example, the total weight of the pipe in the air is equal to the around 89 kilonewton. Total weight in the water is 6 kilonewtons. And the next slide shows also other steps. And this figure shows the depth, depth of the water, for example, distance between the water surface and seabed level is 80 meters. And we know the pipe where the valve is located in the middle of the pipe is exactly on the top of the pit. So the distance between the valve or 60 buoy and the bottom of the pit is 20 meters. So the total distance from the between the bottom of the pit and the water surface is 100 meters. And this yellow color is the material property of 60 buoy. Shows the weight of the valve outside of the water, which is 196 kilonewtons. And the weight in the water is 186.081 kilonewton. I use this value of force as a normal force on the SolidWorks FEA to do the stress analysis based on this weight in water. This weight in water is the weight of the 60 buoy or valve inside the water. So this slide shows the OrcaFlex platform. The first figure is the OrcaFlex platform before running the simulation. This red color is a vessel. This yellow color is the pipeline. And this red color in the middle of the pipeline is a 60 buoy or the valve. And this is the pit. We know the valve or 60 buoy is exactly on the top of the pit. And the second figure is showing this simulation after after running the simulation. So did you guys see these two white colors? These two white colors, I mean, exactly the yellow color, which is the pipe, the length of this yellow color is 20 meters. We are just focusing the stress analysis of exactly these 20 meters of the pipeline. That's the reason I used or I designed the pipeline in 20 meters length because of these 20 meter lengths of the OrcaFlex. So we are just focusing of the all stress analysis exactly in these 20 meters of the pipeline. So let me show you guys the OrcaFlex dynamic video. Yeah, showing the properties of the 60 buoy. You know, the weight of the 60 buoy inside the water. Now I'm running the simulation. Yeah, it is showing the process step by step. Yeah, that's so it's pretty much like this. And now in this slide, I'm gonna talk about the SolidWorks FEA model. So finite element analysis, FEA, is an accurate method for numerically solving differential equations to simulate the actual assembly parts by representing them into small elements called the objects meshing FEA. FEA software is an essential tool to simulate the failure behavior of a pipeline by applying different loads and investigating the reason for failure of an offshore pipeline. The result of the finite element analysis is entirely relying on the design, geometry shape, material properties, and boundary conditions of the model. The offshore pipeline is designed and structurally analyzed with the SolidWorks 2021 modeling software. In this project, we are looking for the stress analysis of the specific part of the pipe that is located exactly in the middle of the offshore pipeline. The SolidWorks simulation section determines the categories such as the maximum volume stress, which is also called distortion energy, stress at node 20, and maximum displacement are examined and analyzed by applying force on the pipeline. That we know that I said from previous slide, I use normal force value from the OrcaFlex, the weight of the 60 buoy inside the water. And so this slide is about the meshing and fixed surface. The first picture is my design in the SolidWorks FEA, and this point is the point where the force, normal force, is located in the which is in the middle of the pipeline. And we know this value of the force is 186,000 newtons, which came from the OrcaFlex 60 buoy weight in the water, and the material is stainless steel, which is very strength, has a high yield strength. And the second figure is a meshing. And these two yellow or golden color is the fixed point. I apply the fixed to the wall thickness of the pipe. The reason I use the fixed point to prevent any rotation of the pipe, because if I do not apply the fixed point and apply the normal force and then running the simulation, the pipe is rotating and the software doesn't give me any result. That's the reason I use or apply the fixed point to prevent any rotation and give me the result after running the simulation. And we use the meshing to transfer the load to the finite element model. Meshing element act as a three-dimensional springs and provide accurate result in a short processing time. And also in the meshing has a two section. One is a fine and the other one is a coarse section. Fine, it takes more time to computing the process. However, the result is way more accurate. However, in the coarse section, the computer software or the simulation software is computing so fast. However, the result won't be as accurate as the fine section. In a result, so this slide is about my manual hand calculations or engineering hand calculation. I use the solid mechanics equation. So I calculate the maximum bending stress and maximum displacement by the manual hand calculations. So for calculating the maximum bending stress, we need the force, we need the C, we need the length of the pipe, We need the maximum bending moment, we need the external and internal diameter, moment of inertia, and then we can find or calculate the maximum bending stress. We know the force is a 186.081 kilonewton. I use this force as a normal force to the SolidWorks, and I use this value from the 60 buoy weight in the water on the OrcaFlex. And let's see, we know the distance between where the normal force is applied and the origin point, which is equal to the 0.161925 meter. It is the half of the external diameter of the pipe. And the bending moment is equal to force times length of the pipe divided by 4. We know length of the pipe is 20 meters, divided by 4 is 5. But here I made a mistake. It's a typing mistake. It should be 5 meters, not 10 meters. But anyway, the maximum bending moment is equal to the 930,405 Newton meters. And moment of inertia is equal to pi over 64, then times into the parentheses, external diameter to the 4th power minus internal diameter to the 4th power. We know moment of inertia of each shape depends on the geometry shape is different. My project is about a pipe, and we know the pipe, the geometry shape of the pipe is a cylinder. So the moment of inertia of cylinder is this equation, which is pi over 64 times OD to the 4th power minus ID to the 4th power. And the value of a moment of inertia of the pipe is 1.37807 times 10 to the negative 4 meter to the 4th power. But, and anyway, and finally, the maximum bending stress is equal to the bending moment times C divided by the moment of inertia, which is equal to the 10,932,378.59 kilonewton per meter squared. This is a really big number. Believe me, this is a huge number. And also, when I doing the analysis, my result from the simulation analysis of the OrcaFlex and SolidWorks, it is also big number. And the maximum displacement, calculating the maximum displacement, we need the force, modulus of elasticity, moment of inertia. The modulus of elasticity, or Young's modulus, is equal to the 2 times 10 to the positive 11 Newton per meter square, or 200 gigapascal. And we know the moment of inertia that we discussed in previous slides about the maximum bending stress. And the equation of a maximum displacement is equal to the force times length of the pipe to the 3rd power divided by the 48 times modulus of elasticity, then times moment of inertia. The final value of the maximum displacement is equal to 112.5 millimeters. In a simulation processing, the total of 5 cases in different degrees were simulated to analyze the maximum wall mass stress, stress at node 20, and maximum bending stress of the offshore pipeline. I used the 5 different degrees in an OrcaFlex, in a dynamic case. Those 5 degrees are 5 different directions of the wave. Those degrees included 30, 90, 150, 180, and 215 degrees. So this is a post-processing script of the dynamic case. If you see, we have 5 cases, 1, 2, 3, 4, 5. These 5 cases are the 5 degrees. So that we are looking for the one mass stress, stress at node 20, and maximum bending stress of 5 different cases. We use these processes for the static case, but just one case, because in a static case, no wave velocity, no wave vibration, no wave current is included. So we have just one case because we know the wave direction of all degrees or all angles or direction of the static case is going to be the one value, one result. In the dynamic case, we have a different result because in different degrees, because of the waves current interactions, because of the vibrations. We know in a OrcaFlex, we have a pre-processing script, post-processing script, and result script. So this figure or this chart is the dynamic case result for the 30, 90, 150, 180, 350 degree for the maximum wall mass stress, stress at node 20, and maximum bending stress. And the minimum value for the maximum wall mass stress belongs to 180 is equal to 185,052,061.86 kilopascal. And the largest value belongs to 215 degrees is equal to the 185,064,119.74 kilopascal. This is a huge number. But I want to say something with you guys. Yes, in a dynamic case, we have a different values for different directions, wave direction. But in overall, they are not really huge differences. Yes, there are differences, but not that big difference between the angles. In a static case, all these processes like dynamic case are followed. However, the values of variables of maximum wall mass stress, stress at node 20, and maximum bending stress at different degrees will be the same. This is a chart for the static case. The value of a maximum wall mass stress and stress at node 20 are equal to each other, which is equal to the 1.347 times 10 to the positive 5 kilopascal. And value of maximum bending stress for the static case is equal to the 5,336,932.02 kilopascal. These are the result of the either dynamic and static case of the OrcaFlex. And we know for the comparison, we are just comparing the value of the either SolidWorks FEA analysis result and the hand calculations with the static case result of the OrcaFlex. We don't compare the dynamic result of the OrcaFlex with the SolidWorks and the hand calculation. Just static case with the SolidWorks result and hand calculation final result. In a SolidWorks result, I want to say, so in a result of the parametric and simulation study in the SolidWorks 2021 final element analysis provide tables to clearly understand the wall mass stress and displacement where the valve is located in the middle of the pipeline. In a simulation study, the mesh side is closer to the core section because it helps to reduce the computer processing time and prevent computer calculation errors compared to the fine section. However, the result from the fine section is more accurate compared to the core section. And the stress analysis result predict the failure behavior by accurate criteria such as the maximum wall mass stress, stress at node 20, and maximum displacement of the different nodes. The force result from the OrcaFlex 186.081 kilonewton is applied to the SolidWorks model, and the simulation analysis on SolidWorks result provided the values of the maximum wall mass stress, the stress at node 20, and maximum displacement. And also we learned when the more wall mass stress is gonna be more displacement. More stress means more force applied. Anyway, so these slides, we have two figures of the maximum wall mass stress and displacement. This is for the wall mass stress and this for the displacement. The red color means more wall mass stress is located. And this red color means more displacement is located here. We know more force, more wall mass stress. Obviously, more wall mass stress means more displacement. We know stress and displacement has a directly proportional to each other. And the maximum wall mass stress is equal to the 2.072 times 10 to the positive 8 Newton per meter square. And a stress at node 20 is equal to the 1.293 times 10 to the positive 8 Newton per meter square. And maximum displacement is equal to the 242.1 millimeter. You know, working with the SolidWorks is so exciting, and I love working with the SolidWorks, either finite element analysis or CFD or heating analysis. You know, this is very amazing software. And let me show the video of the one message simulation. So I'm running the simulation in this video. This is an animation of the one message stress. Yeah. And the next slide is about doing the simulation or running the simulation for the displacement. So this is the animation of the displacement. Goes up and down, shows the different colors of the blue, light blue, green, yellow, and red. Red means maximum displacement, which is located in the middle of the pipes. So in this slide is about the comparison of the results. In this, we know the equation to calculate the percent error is equal to the higher value minus the lower value divided by higher value times the 100%, times 100. So the percent error of the OrcaFlex stress at node 20 and SolidWorks stress at node 20 is 4%. And the percent error of the manual hand calculation of a maximum bending stress and an OrcaFlex maximum bending stress is 51.18%. And the percent error of the OrcaFlex maximum one message stress and SolidWorks maximum one message stress is equal to 34.99%. And the percentage error of the manual hand calculation of a maximum displacement and SolidWorks maximum displacement is 53.53%. This slide is the main purpose of my project, to compare their analysis results of the two softwares together, as well as comparing softwares with the hand calculation to see how much percentage error difference between two softwares together or between the hand calculation with the softwares. This is the main purpose and amazing part of my project. And it's going to be very useful in your research or in the industry. We need to doing the comparison result to get a better result or to get a better decision of our project, or doing any research or doing any research before any practical installation. We need these methods. These engineering methods. So in the conclusions, in this project, the simulation stress analysis method is used as an essential tool to simulate the failure behavior of applying loads and investigating the reasons of pipe failure. And we learned the purposes of using analysis method results are to minimizing any injury, damages, financial, and time waste before starting practical engineering model installation, as well as minimizing the manufacturing, processing time, and eliminating all reworks and delays. Simulation software such as the SolidWorks FEA 2021 and OrcaFlex 11.1 dynamic analysis is used to calculate categories such as the maximum one message stress, stress at node 20, maximum bending stress, and maximum displacement on different axes on different nodes. So we learn when more forces, we have a more one message stress, as well as we have a more displacement. We know one message stress and displacement has a directly proportion to each other. The completion of the analytical calculation, the OrcaFlex dynamic and static case, SolidWorks FEA as well as manual hand calculation used to compare provide the accurate result of failure behavior of the offshore pipeline. We know in an OrcaFlex, I use two cases, dynamic and a static case. The difference is the dynamic behavior of the pipeline was studied under the wave and current excitation. However, in a static case, all the stress analyses are analyzed without the influence of the waves and current interaction. It is evident from the study that dynamic stress due to the action of waves and current is amplified and increased compared to the static stresses. And also, I want to say, we learned in a comparison, we compared the SolidWorks FEA final result and a manual hand calculation result with a static case, not with a dynamic case. Because in dynamic case, we have a different degrees in different directions and different results. So it is impossible to compare the dynamic results with the static result of the SolidWorks and the hand calculation. So we just comparing the static case result with the manual hand calculation and SolidWorks FEA results. And I want to say, I really enjoy to work with OrcaFlex. It is really accessible to work with. It is not that complicated to work. And it is very useful in the oil and gas industry, in submarine industry, whatever relates to the offshore or ocean or sea. It is very, or Gulf, whatever it is so useful to work with the OrcaFlex, and it is very accessible. Anyway, I have a recommendation to decrease any failure behavior distribution, to reduce any crackation or damage distribution to the pipe. We need to increase the wall thickness, because when we increase the wall thickness, it will defect or decrease the failure distribution of the pipe. And at the end, if we want to get more accurate analysis result, the pipe or design must not be complicated in assembly parts, because the software means SolidWorks FEA software gets error in computational errors. So that's it. Really appreciate, guys. Thank you so much. Thank you for your listening, and thank you for your patience. And I hope my presentation be useful for your guys. Thank you, and have a wonderful days. Have a great one.